What's the density of water in SI units? Let's see the responses. Most people say 1,000. So the way I think about that is, so actually there's something called CGS units, centimeters, grams, seconds, and it is 1 in CGS units. Density of water is 1 gram per centimeter cubed. But we're using SI units, which is MKS, sometimes called meters, kilograms, and seconds. And when you do that conversion, it doesn't work out. You get 1,000. And the other thing I think of is if you had a bathtub that is like 1 meter by 1 meter by 1 meter, it's probably more than a kilogram of water in there, right? I guess I would guess probably around 100 or so, but it turns out to be 1,000. It should show up on your phone. Here's my measurements. Knowing all of this now what we're doing is looking back in hindsight, and we're wondering what we should have written down as the uncertainty on each of those time measurements. Most people were saying B, 0.05 seconds. So what I was looking for, because we know I kept on getting different answers. If I had gotten the same answer each time, I think then A would have been correct, because it's half the last digit that's displayed on my stopwatch. But it's the knowing all of this part, right? Knowing that every time I measure it, I get kind of a different number. The actual uncertainty is related to the scatter. You wish to know the time it takes to travel from Finch Station to Young Bloor by subway. You ask 10 people, this is your first measurement, and take a stopwatch and time the trip. You analyze all the data, and you conclude that it takes an average of 26 minutes and 40 seconds. And you also correctly compute your uncertainty, maybe using standard deviation or something, to be plus or minus 100 seconds. So you are applying for funding to expand your survey and go ask 1,000 people the same question. And as part of your grant application, you want to say, well, what should be your new uncertainty in the time it takes to get from Finch to Young Bloor, assuming, again, Gaussian statistics, which I'm not sure apply to the TTC, because there might be lots of weird things that happen in the TTC. But if it did, what would you expect to be the new uncertainty? Responses. A lot of people are saying 10 seconds, and that's sort of my idea, is that you have now, it's like you're doing that measurement of 10 people, but you're doing it 100 times. And then you're going to take an average of those 100 times. And so your uncertainty in the mean should decrease the uncertainty of one of those 10-person measurements by a factor of the square root of 100. So you should get 10 times better uncertainty. So I liked that number. I'm thinking that, again, the uncertainty in one measurement of 10 people is U sub x, and the uncertainty in the mean, if you did it for 100 times, because 10 times 100 is 1,000, that you could reduce it down to 10. Let's say that you made some calculations or something, you did an experiment, and you got 7.056 plus or minus 0.705. So if you're going to publish that in a journal, which of these 3 choices would be the right way to publish that? So either A or B, but not C. I like it. So the reason I like that is, my first thing is that it should be, so the first thing you want to do is round this uncertainty. So you can either do 0.7, that's what I would tend to do, or if you're really writing a careful paper, you round it to 0.71, because 5s tend to round up, in my opinion. And then if you use 0.07, you should round the 7.056 to the nearest 10th place. And if you use 0.71, then you should round the 7.056 to the nearest 100th place. So it depends how you rounded the uncertainty to give you how you round your value. So that's really good.
So you make salt water by pouring 2 packages of salt into a container of fresh water and then stirring. You measure the mass of the salt from the first package to be 13 plus or minus 0.2 grams. You measure the mass of salt from the second package to be 4.4 plus or minus 0.1 grams. And you measure the volume of fresh water in the container to be V is 1.72 liters plus or minus 0.02. The salinity, calculate the salinity of the water in grams per liter, where the equation for salinity in this case is S equals M1 plus M2 over V. So, okay. So the first thing we can just do is calculate the value. Question 1 is the value, question 2 is the uncertainty. So let's do that first. S is just going to be 13 plus 4.4 divided by 1.72. Easy marks. Open bracket, 13 plus 4.4, close bracket, divided by 1.72, equals 10.116. And that is going to be grams per liter. So the answer to question 1 is D. So there's a point right there. And now the uncertainty. So what we're going to do is we'll, set, M equals M1 plus M2. So the uncertainty in the mass is going to be the square root of the uncertainty in mass 1 squared plus the uncertainty in mass 2 squared. When we're adding things up, that's the rule for sum or differences. So you just get 0.2 squared plus 0.1 squared square root. Uncertainty in the mass is equal to square root of, open bracket, I got 0.2 squared plus 0.1 squared equals 0.05, take the square root of that, and I got 0.2236, and that's going to be in grams. And then we're dividing two things, so the salinity is equal to, remember, the total mass divided by the volume. So the uncertainty in the salinity divided by the salinity is equal to the square root of the uncertainty in the mass divided by the mass squared plus the uncertainty in the volume divided by the volume all squared. So I would say the uncertainty in the salinity is equal to the salinity, which we already calculated, it was 10.1. 16, I'll put times the square root of 0.2236 divided by that total mass, which actually I never calculated. Mass total is equal to 13 plus 4.4, so it's actually equal to 17.4. 17.4 squared plus uncertainty in the volume, which is 0.02 divided by the volume, 1.72 squared. You got to be a little careful with your calculator. Open bracket, 0.2236 divided by 17.4, close bracket, squared, plus, open bracket, 0.02 divided by 1.72, close bracket, squared, equals square root of that times 10.116. So the uncertainty is 0.175, and that's grams per liter. So the closest one, I would just round it up to 0.2. Question 3. The number 0.0003 has some number of significant digits. So this is placeholder, placeholder, placeholder. This is significant, 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 and significant. So I would count 4 here. So that's C.